So coulombs per Newton.
No, don't. All right, so this is coulombs per square meter divided by coulombs squared per Newton
Okay.
squared.
So
You were close, you forgot something.
okay. I'm trying to work through it. So 1 coulomb cancels the meter squared. What did I forget? Just 1 coulomb cancels. The meter squared cancels. Okay. It's not coulomb per Newton.
It is not,
Is it newtons per coulomb?
it is Newton.
That's
yeah.
based on memory. I did not
Gotcha.
work through
No,
whatever you're doing.
I should have, yeah.
But it's also, it's 1 over this, so it flips.
Gotcha. Okay.
And it's also electric field, so you can also go off memory of what the units for electric field are.
That's
Okay.
my strategy.
Thank you.
All right, so is that because of the plates or the total?
That is the plate, right?
So 200 newtons per coulomb. What about the total electric field between the plates?
So the 8.85 times 10 to the negative 12th is E sub naught. That's not, or is
Epsilon sub
epsilon
naught.
sub naught.
Right.
Not,
Permittivity of free space.
okay. I don't know. I think I'm at a wall here.
So it says the formula you have written just has epsilon in the denominator for the total electric field, which you said implies there's something between the plates, but there isn't anything between the plates. So is it equal to the electric field of the plates?
Yes,
in
it
this
is.
case?
That makes sense to me.
All right. So that's basically the way that this kind of problem works.
I like these
I'm going to take these equations just for board space because I want to keep the old answers up here, and I'm going to write the equations, in essence, off camera screen, which should not affect you. But for all the fans watching at home and for people who aren't here today, I'm about to write this over here, so make sure you have pause it, write it in your notes if you need to. So we have C is equal to Q over delta V. C equals kappa epsilon sub naught A over D. Delta V negative D dot X. Sigma is equal to Q over A. It's not, and this is for the plates. And, oh, I guess we have epsilon is equal to kappa, epsilon sub naught. I think I got them all.
Are any of the formulas that you have written on the side of the board things we need to know cold, or are they things that will be available to us in a test
Both.
setting?
It'd be really good if you know it cold. However, they would be at the top of the page.
In case we totally blank out, it
Yep.
is an option. That's
Yep.
good to know.
The main reason why I suggest you know it cold is, you know,
Time.
what was that?
Time.
Not just time, but you know, if your brain kicks into panic mode in a test, and suddenly you're looking at all the letters and going, "Wait a second, I don't know what the letters mean," or you're looking for, you see the C and suddenly think that it's coulombs instead of capacitance.
Right.
Or I guess the biggest one is, there's a 110 quiz where they do centripetal motion and angular momentum, and both of them have M, V, and R in it, different combinations. And the students who don't know it cold come in there and they just grab one of them. 50% chance of getting it right. So now, I'm going to change this. I'm going to stick a dielectric in between. And the dielectric, not a free space anymore. The dielectric constant, we're gonna make 2. We're already using 2 over there. Let's make it 4. All right. So first off, what is going to stay the same?
Voltage.
Yes, and that is an important thing to recognize. Voltage will stay the same. Why does the voltage stay the same?
Because we haven't done anything to the power supply, it's still the exact same power supply.
Yep. So that's now a 4. There's one other thing that is going to stay the same.
Area of the plates.
Besides the physical, there's one other of these that is going to stay the same.
The capacitance should stay the same, right? Because that's based on.
Yeah, if the capacitance stays the same,
yeah.
then use of the dielectric becomes almost meaningless.
You're right. You're right.
Well, let's just take that. If the capacitance is going to change, what has to change in order for the capacitance to change? If you think back to what the formula is for capacitance,
Q obviously has
yeah.
to change.
So we'll be able to store more charge with the dielectric. So dielectric actually has twofold purpose. One, it allows the plates to get closer together without touching, and 2, it allows more charge. But I'm not, I put a thick dielectric in there. That's a 5 centimeter gap. About a 2-inch gap between those plates. All right, so
Will the electric field for the plates stay the same?
no, because the electric field for the plates depends upon the charge density and surface charge density, and that's going to change. However, go for it. Okay, never mind. We were not in sync just then.
It seems like you're hinting that the total will stay the same, but that the electric field for the plates would change. Is that what you're getting at?
Yeah, the total will stay the same.
I can't answer why, but that's,
My voltage stays the same, the distance between the plates stays the same. This is the total electric field. This is the electric field that you're going through as you go through the dielectric. So the total electric field will stay the same. And now we're left with the others. So let's go about solving. In order to find the capacitance with Q over delta V, we need to know Q, so that way it's not going to work. So what do we do? How do we find, we can find capacitance at this point. Brooke?
Do we need to use the kappa to find capacitance? Do we need to use the kappa times area times epsilon sub naught over distance?
Yes, that one will work. Because I know all of these quantities now. The only thing that's changed from what I had before is kappa is now 4 instead of 1. And so my capacitance should be, well, if everything else stayed the same, 4 times what it used to be. So 28.32 times 10 to the negative 10 coulombs. Farads. Or 2.832 nanofarads. Yes, Brooke?
How did the dielectric constant, how did kappa change?
I put a dielectric. Before you came in, it was just free space in between it, and then I stuck a dielectric in the middle.
So now the permittivity has changed.
Right.
Okay,
Yeah.
thank you.
Yep.
Dr. Fox, I'm
Yes.
still a little confused on that, because before you had written the 8.85 times 10 to the negative 12th, right?
Right.
Up above, but then you erased it and changed kappa. I guess I'm just a little confused about the connection between the dielectric constant and the permittivity? I know they're related, but I'm missing something.
All right. So, at some point they figured out that that if I have nothing there, the permittivity is how a medium reacts to an electric field, in essence. So with nothing there, I'll put nothing in quotation marks, it reacts to we get a value of 8.85 times 10 to the negative 12.
Right.
Coulomb squared per Newton meter squared.
And is K always equal to 1 if we're dealing with free space?
Free space kappa is always equal to 1.
I'm sorry, thank you.
Yeah, we got too many other K's.
Right.
Now, if you use paper, for example, and I look it up every year, so I'm going off of memory on this one, but I think for paper, kappa is somewhere around 1.5-ish. There's a range depending upon other factors, but so this is epsilon of free space, epsilon of this mythical paper I'm doing, where kappa is equal to 1.5. It would be just 1.5 times that. So roughly 13.5 crudely, times 10 to the negative 12 Coulomb squared per Newton meter squared.
Okay. So ultimately, when we plug in epsilon, when we're solving for the electric field, we're just going to multiply 8.85 times 10 to the negative 12 by 4.
Yes,
I see, okay.
and that is it's just easier to keep track of kappa than have to keep track of
Mm-hmm.
whatever that number really is,
Right,
the
right,
full
right.
number for all these products.
Got it. Thank you.
Yep.
I had a question. Is the reason you might have said this that it's not 200 newtons per coulomb for the new
Was that your issue?
Yes.
Okay, thank you. In unison would have been really cool just then too. Just so you know. You fool, you made a mistake.
You made a mistake.
How could you?
How could you?
Who raised you?
Who raised you?
See, next time.
Yes. I'll
The
know
whole
for next
class
time.
together.
Yes.
By the way, if you wish to insult me to my face, I'm fine with it as long as you do it with the voice of Mr. T.
The voice of what?
Mr. T. If you don't know who Mr. T is, look it up or ask your parents. I had one student years ago who would call me a fool in her Mr. T voice. It amused me. Anyway, so the electric field from the plates, how does that change? Or charge? Charge might be easier at this point. What is the charge?
Isn't it gonna stay constant on the plates?
No, charge is not going to stay constant. If I disconnected the battery, the charge would stay constant, but I have not disconnected the battery.
I got 2.832 times 10 to the negative 9.
Right.
That would make sense.
Yeah.
So you just multiply the charge by 4?
Oh no, I plugged it into the full. But I guess yes, that's basically what I did. Yeah.
Yep, it should have, sorry, puberty. 28.32, is that what you said?
Yeah. So yeah, same. Okay.
Times 10 to the negative 8th. I guess 2.832. Units?
That's the coulombs.
All right. And so what happens to the electric field from the plates now that I've quadrupled the amount of charge on the plates?
Wait, I'm sorry. I don't understand why it's to the negative 8th and not to the negative.
You put the
9.
decimal after.
You just changed the
Yeah.
decimal.
Another opportunity you had and you missed it.
Then it should be 2.8, right? Not 20.
If it was 10 to the negative 8th, it would have been 2.8. Or it's 28 times 10 to the negative 9th.
Because it's just the capacitance times 10.
In this case.
Right. Yes.
What did I do wrong?
I'm feeling more confident with what I've written down now.
And you feel less confident.
I feel less confident
That's
now.
so sad.
What did you get when you?
I got 2.8 times 10 to the negative 9.
Oh, that's because you've got 2.8 instead of 28. So you are correct.
Right, so he should be the decimal, right?
He could, but I think he's just keeping it because he's got 28 point whatever for the capacitance up top.
Well, I did it also just, I multiplied that by 4.
But then that would change the exponent.
All right, but we're differing by a factor of 10.
Yeah. Let me.
Oh, it could be how you typed it into the calculator?
Yeah, let me see. So I did 4 because I was just plugging it into the. Oh wait, no, I was doing the wrong formula.
Nope.
I was in the wrong formula. That's what it was. I think.
Okay. You were solving for capacitance?
I was
instead of
solving for
coulombs?
I was solving for capacitance.
Okay,
Yes.
which then, therefore your answer matches what we have at the top.
Yeah,
Okay.
that's what I was doing. Okay.
Since we're on a roll with mistakes going on, any other mistakes on the board? I'm assuming this is solid gold.
Looking great.
All right, there we go. All right, we have the one last gap here, the electric field. Because of the plates.
Well, we need to do sigma using our new charge.
Okay. So,
Well, you
So-
are very conveniently standing in front of the formulas, so I cannot
Yeah,
use
we
them.
don't
Oh, yeah, right.
Go.
So we're gonna do charge, our new charge divided by 4, since that's still our area, which Harrison is currently whipping up. And then we'll take that number and,
Oh, so it's just our. Yeah, so it's just gonna be our previous
right.
charge, right? Yeah. Yes, it's gonna be our previous charge.
Well, the 28.32 times 10 to the negative 9, debatably.
Right,
But
divided
see, but since we
by-
have something in between now, we can't use it. Oh, we use our different epsilon number. We use this,
epsilon sub 0?
no, we wouldn't, right? Because now there's a, dielectric, so we can't use epsilon sub 0.
The electric field from the plates still sticks with epsilon sub 0.
Oh,
The total electric field changes, that's where you're using epsilon, but from the plates, it's still epsilon sub 0.
if the total changes, why have we kept it the same over here?
The total stays the same.
The plates changes.
Yes,
So instead of epsilon sub 0 for the plates, we're going to use the
epsilon
epsilon
sub
that.
0. No.
Wow.
All right.
So long.
Remember that the total electric field, if you flash back to Wednesday, I've got positive plate, negative plate, the electric field going across here, and the magnitude of this is sigma over epsilon sub naught. That's where we started. We did Gauss's law, we derived it for one plate, and then with 2 plates, it's just double that. The dielectric that we stick in between creates this sort of counter electric field because the atoms inside the dielectric polarize.
Right.
So the total electric field is we have this electric field from the plate minus the electric field from the dielectric. That gives us the total. That total is still 200 because our voltage and the distance stayed the same using that formula right there. So if I think of this as, let's just make that the positive direction. Actually, it doesn't have to be. So my total electric field is the electric field from the plates minus the electric field from the dielectric. This stayed the same. These two did not. From the plates, the electric field from the plates depends upon the surface charge density, which depends upon the charge, so that's Q over A epsilon sub naught. I have put 4 times as much charge on those plates. So the electric field from the plates is over this, the major electric field that's shooting across is now 4 times stronger.
So it's 800 newtons per coulomb. Okay. So we really could just, so instead of like going through the whole process of the formula, we could have just multiplied all those things by 4.
As long as you know which things to multiply by.
Which, as long as we know which
Yes.
things to multiply.
And so therefore, we could also throw in what is the electric field, because the dielectric, or the magnitude would be 600. Or negative 600, it depends on how, lots of different wordings of the question. But a dielectric of 4 is a pretty strong dielectric. I mean, it's, industrial purposes would have something bigger, but 4 would be pretty big for something I can just find lying around. So that's creating this back electric field, counter electric field, oppositional electric field of 600 newtons per coulomb. Brooke, you have your hand up?
I did, but you kinda answered my question. I was just wondering where the electric field of the dielectric would come into play. But we know the total and we know the charge of the plates now, so
Right.
we can find the dielectric that way. Okay.
So is there a situation in which the total, like, so the total would change if we moved the distance, or if we moved the distance, is that right, between the plates? Or when would the total change, I guess?
The total will change, okay, let's do it.
Okay, I guess because I just don't want to get in a habit of like memorizing what's gonna stay
Yes.
the same.
That's a good idea, not go into memorizing all of it. I mean,
Yes.
being able to, given a problem like that, and there will be one on the test, let me just put it out there.
Yeah.
Knowing how to apply the formulas, and then the 2 basic principles of, if the battery is still attached, the voltage is fixed. If I do a nice perfect disconnection of the battery, the charge is fixed. So let's disconnect the battery now.
Okay, let's do it.
So we still have that dielectric in there. And before we continue, any other questions before we start looking at a different situation? Let's give ourselves some room.